I'm pretty sure all of you know this, most of you anyway. An ADCP will measure a portion of the river, but not the entire river. So we need to extrapolate the data to know how much flow there is. And in the ADCPs from various manufacturers, this is done by fitting the measured data to a theoretical vertical velocity profile to get the entire discharge, excluding the edges, but I'm not worried about them right now. In the good old days, when we had only Wind River, this was the tool we had to help us to extrapolate the data. It was not very easy to see whether the extrapolation default values were correct or if we should use something else. In part because all sorts of ADCP data is noisy. And in part because of the default colors in Wind River. That yellow was the bad there. It's just as visible on my screen as on the screen here. And another thing, what we generally tried to do to make something out of it was to average. And with an ADCP and Wind River, you can only average across the bins at the same depth, which means you would have to average over a portion of the river with the same river depth. Because what you really want to see is the shape of the velocity profile, and that's depending on the relative depth more than the absolute depth, in theory anyway. And if you try to average from a deep part of the river into a shallow part of the river, then you will take the bottom velocities here and try to average them with the mid-depth velocities here, and that's wrong. So then USGS made a software called extrap, and it does exactly what the other software did not, to plot the relative velocities versus the relative depth. And if the shape of the velocity profile is the same all across the rivers, those dots will fit nicely into a curve showing the velocity distribution in the vertical for the entire river. So this made it a lot easier for us to trust that we could change the default extrapolation values in Wind River. And we got this. This shows the methods used to extrapolate the data in our database since 2007 till 2015. The blue line, that's the default values in Wind River. A power law set divided by depth raised to the power of 1/6. That's the default. And it was used in almost 100% of the measurements before we started using extrap. The first beta version of extrap came in 2009. You can see the blue line going down. That's the default extrapolation. The green and the red ones, that's not default extrapolation methods, it is other methods. Then we had the first release version in 2010 and a way better version in 2012. And you can see this red line here. That's the new truth, more or less. That's the power, now the constant no-slip extrapolation, where we tell the software to assume that you have a nice curved shape up to the lowest bin, and then a straight line from the highest bin to the surface. And it seems now it stabilizes at 50–60% of our measurements will have that sort of extrapolation. And this affects our computed discharge, which in turn will affect the rating curves that we make from these discharge measurements, which in turn will affect the total runoff from Norway, which in turn probably will either mask out or make us believe that there are some climate change going on. So we want to be sure that if there are any trends in our time series, that's because of a change in the nature, not because of a change in the processing. That's why we're looking so much into this. Anyway, for 902 discharge measurements, we have compared calculated discharge using the default extrapolation and the actual chosen extrapolation. And it seems that the median value is that the discharge is down by 1.5%. For the 60% of the measurements that are constant no slip, the discharge is down by 2.6%. So it's not a lot, but if this leads to a change in discharge or runoff from Norway of 2% over a 5-year period, that would start to alarm some of our climate researchers. And I showed this to some of our climate researchers and asked them, do you want a consistent time series or do you want a correct time series? And I needed 2 weeks to think about it. And I said I wanted what we at any time think is the correct time series, but documentation on any systematic change in it. But even before I started looking more into this, I saw a presentation by one of Calvin's colleagues, David Mueller, at the Hydroacoustic Work Group at the Office of Surface Water in the US Geological Survey. And he had done some field measurements and some computational fluid dynamic model things where he calculated the flow around various ADCPs and mounts and found out that some of the instruments influence the flow around them quite badly, in part because they just break, what is that in English? Retardation. It slows down the water. That's part of it. And in part because it bends the flow across the instrument. And the beams going out like this, and the flow going like that. The flow is more perpendicular to the beams, which leads to even lower reported velocities by the ADCPs, because they cannot measure velocities perpendicular to themselves. So there's a double effect of this ADCP we are sticking into the river that will make the ADCP report a too low velocity near the surface, or near the instrument, I mean. But I did not really believe this, because it couldn't be that bad. This was just some computations and some few measurements in the river to confirm it. So I can say this first. The result from Davis' studies was that there was a quite bad flow disturbance around the Rio Grande and the M9. It was less impact on a river ray, and there was very little impact on the stream pro. Are everyone present familiar with these instruments? Yes. So that's what I was going to say. We did some tests to prove him wrong. And shall I spoil the conclusion? No. We tested the Rio Grande, the stream pro, the river ray, the river pro, the river. Lost it. Rio Grande, stream pro, river ray, river pro, Rio pro, M9. And we tested them on a trimaran, the big for the stream pro, the small for the stream pro, the default one for the Rio Grande, and the new default ones for river ray and river pro. And we tested it in the Rio Grande anyway, and the fixed mount that we used on our inflatable boats. And we used an ARC boat, that's a remote control boat from HR Wallingford in England. And we tested it on a torrent, on M9, on a torrent board with a RQ pod outfit. That's just a small controlling unit and 2 small propellers, so we have a radio control boat on that one as well. And we tested them in front of the inflatable boat, on the side of the inflatable boat, the remote controlled boats, of course, by themselves. And we tried to do it in fast, medium, slow, and super slow water. And how did we do this? Well, this is just pictures of different mounts. The one up there we have never used. So the way we did it, it's quite hard to find a river where we can test all of these instruments in a timely manner. So what we started thinking was, okay, what if we want to test it on a location where we know the velocity profile? Because whatever you put into a river will do something about the flow pattern there, more or less. But if we measure on a perfectly still lake, we know the velocity profile. It's 0 from top to bottom. So instead of having a standstill instrument on a moving river, we have a moving instrument on a standstill lake. And then when we drive across, the instrument and the boat will pull some water along, and that will be equivalent to if the boat was standing still and the water was moving. Only that it will be the worst case scenario. Because in a river you will have turbulence, and turbulence will mix everything you throw into it, including velocity gradients. So the velocity gradients will die out faster in a turbulent river than in a perfectly calm lake. So we tested for the worst case scenarios here. But even in a lake, you will have some circulation. So we chose a lake nearby where one of my colleagues lives, and he could just look at it with his eyes. When there are ripples, waves, when you feel the wind, he knows that it's not still. So we looked for an occasion where there had been no winds for many days, and no precipitation either, and no snow melt. Wind was the worst problem because this lake has a very, very small catchment area, so there's little water running through it. Yes, still water, like I said. More often than not, this occurs when it's cold. Yes. Just more or less right before the lake freezes over. To document, the lake might look like this, and it did all of the days we started working. But we wanted to prove that the water was still, or almost still. We took one of the ADCPs and anchored it, just left it there for half an hour, several hours, calculating bottom track referenced velocities to see if there was any movement. And movement is not a very big deal, but if there is a gradient, that's a big deal. So we wanted to look for days where there were no gradients in the water. Unfortunately, we do this at the same time as we measure, so we don't find out until after we finished that, okay, we shouldn't have done it that day. But anyway, this was from one of the first days. We see there is a small velocity, less than a centimeter per second, and no gradient, apparently, or so to say no. The mean velocity here, that's not the mean of the amplitudes of the velocity, it's the north distance multiplied by the time difference, the delta t, and the east velocity multiplied by delta t, so that you sort of get a distance made good for each water particle, and that should average to 0. If you only use the magnitude, you will never get to 0. That was day 1. Another day, a little bit worse, but still the gradient is less than a centimeter per second. Still less than a centimeter per second. It just looks worse because it's a white plot. This one we could not use. We had a gradient of around 7 centimeters per second. And when we try to measure velocities of 0.3, 0.5 meters per second, that's a lot of percentage of what we are trying to measure. So we could not use that day. And this is a weird one. Very, very weird. I have a bonus slide at the end showing the same from in river. There's a stripe of velocities. This is for Rio Pro. And that big velocity there, that's just when it switches from small to big bins. And I don't know what it is. I have interpolated here so that it doesn't show the actual location of the cells. Okay, all days were good, except one day. Like I said, the velocity gradients, that's what we are worried about. But with 1 centimeter per second, it's okay more or less to look at data of 0.5 meters per second and up. We had quite a lot, not quite a lot, but some runs at around 20 centimeters per second. But we can only use those data for the days with really little gradients in the lake itself. How am I doing on time? I'm talking too slowly or too much. So let's just jump to the actual measurements. This is the Rio Grande fixed. By fixed, I mean fixed on the boat. And this is from the side mount. And we can see that there is a serious backbending here. That means that if this was a river, the velocities would have been smaller close to ADCP than further down. All of the data I show here, you can probably not read it. It's the percent difference in the velocity from a deep bin down here and the other bins. So that up here, the velocities are 10% smaller than at 1 meter and 30 centimeters. 10% smaller up here, 10% smaller up here. On this plot, I've not done it on all of them. I've marked where you have a 2% error, and it's on half a meter, more or less, using a Rio Grande, like we had done since 1995. On the front mount, it was even worse. Only that we didn't measure all the way to the surface, but the lower velocities are way worse there. So the conclusion of this was that we just stopped using these mounts. Unless it's the only option we have. If it's a raging flood and we have to go with a manned boat, then we can use it. But we will need to be very careful when we look at the extrapolation, not to easily choose constant at the top. Okay, Rio Grande and a trimaran, which we have started using after we stopped using those fixed mounts. We just have a pole in front of the boat and the trimaran hanging in front there. That's a lot better. Way less flow disturbance for the trimaran. But still, it is there. For some reason, it's less flow disturbance when we have it on the side of the Zodiac than in the front. I guess that's not a conclusion you can draw for all sorts of boats or all sorts of Zodiacs. But a funny little thing here. Because I would have thought that the Zodiac, which is relatively big, would do something worse with the flow, but it improved it. Okay. Someone suggested that it would be less flow disturbance if we rotate the Rio Grande 45 degrees and mount it like a Stream Pro. And it is a little bit better. The black line, that's when it's on the side of the boat. The red line is when it's in front of the boat. And the blue line, that's when it's in the front of the boat and rotated 45 degrees. So it is a little bit better than have it the original way. But in recent years, we have started to use remote control boat more and more, and they are bigger than trimaran. They push more water away. And this brown-yellow line here, that's for a Rio Pro, but it has the same shape as a Rio Grande. It's just the same housing as a Rio Grande. It's just an upgrade. And we see that that has the worst flow disturbance of these 4 options. Also, we see that it produces more noisy data, because most of the Rio Grande data, that was pulse coherent modes, 5 or 11, and I couldn't make that Rio Pro to stay in pulse coherent. But still, this worries me a little bit, because these remote control boats are insanely expensive, even by Norwegian standards. And we have bought quite a few of them. All of our teams now, that's not a lot, we are a small agency, but we have bought sort of 5, 6 boats like that, and the rest are, well, we have a remote control boat on each regional office for use. And I didn't really like what I saw here, so, and this is very fresh data. I collected the last of these data 1 week ago. So I will advise my colleagues not to use the Rio Grande or the Rio Pro in the ARC boat, the remote control boat, unless it's a very big and deep river where the extrapolation doesn't really make that a big effect on the discharge. And of course, to be careful to use constant extrapolation at the top. Okay, what about the new instruments? Have things got better? Have they got worse? The river ray. On this day, there was some gradient. So there was some small share in the velocities in the lake itself. So we can safely ignore, for these measurements up here, any error that is less than 2%. And on this one, an error that's less than 1%. Because the natural share in the lake was in the order of 1 centimeter per second. So with that in mind, I said the river ray in the trimaran, that works just fine. There's a small backband here, but it's less than 1%. So that is, I have not done any statistical analysis on this, but it's probably within any band of uncertainty you can think of. River Pro in the same trimaran, or same kind of trimaran, that shows a more suspicious pattern. It seems to be more obvious that there is a backband here, but still the numbers are small. Got the line for 2% going up here, so it just barely pokes its nose outside of 2%. So what we are seeing here might be because of an instrument, and it might be because of that small velocity share in the lake. But this was late in the afternoon, and our measurements from the anchored one show that there was less and less and less velocity share the longer in the evening we got. So I think from this slide and the previous one, the river ray, come on, now there. This is like the remote control on my TV. Press once, nothing happens. Press 3 times, and the last 4 things you try to do happens at the same time. Okay, I'll just leave it there. No, still. I'm not touching anything. This is where I stopped talking. Yeah. So if we compare these 2 instruments in the same trimaran, we can see with some doubt that the river ray is slightly better than the River Pro, meaning that it has less flow disturbance. The only difference here is that the river ray, of course, is this phased array with a flat surface, while the River Pro has this 30 degrees thing, angle on it. But it's not conclusive. This indicates, I say at best, that the River Ray is slightly better. But both are okay. And then the M9. This is the M9 and not in the hydro board, but in the torrent board that they sell in Europe. And to my surprise, it showed very, very, very little flow disturbance around it. But it gave me some really strange data when I increased the velocity from 0.5 meter per second to 1 meter per second, which I'll show in the next slide. And I'm not really sure. I stayed awake all night looking at those M9 data. I will not swear that this is the truth, but the best I could do until now, it looked like this. And the 1 meter per second data just vanished out here somewhere. We used it with the archipod with the propellers on. So what it might be is that the propellers, when we rev them a little bit, they just suck water across the M9, giving that weird profile. So my next test with the M9 will be just to remove the propellers and tow it. But still, to my knowledge today, the M9 works very fine when it comes to flow disturbance, contrary to your colleagues saying. So so someone once said that his colleague Dave Mueller, he either says he doesn't know or he's right. So it's I'm a little bit worried to have some observation that contradicts what he had been modeling. So the future will show which is correct. Okay. Now we're seeing different instruments in the same boat. Now we'll see the same instrument in different boats. Does the boat matter? We put the River Ray, no, not the River Ray, the River Pro, and the Arc boat from Wallingford, remote control boat, and into the standard trimaran to see if there was any difference between them. And there was, but it was not a lot. It is still more or less within the uncertainty that comes from the natural gradient of the flow in the lake itself. The trimaran does better, but not very obvious, not very clear to my eyes. But if you want to if you are very, very worried about flow disturbance, you are maybe better off with using the trimaran instead of the arc boat. But this looks equal enough for me that I will not recommend my colleagues to stop using the arc boats. Not based on this data anyway. Okay, and who's missing? Did I forget anyone? The queen of no flow disturbance. We have done several measurements with the Stream Pro, in part because it takes so long to get stable and nice data to look at. These are 15-minute runs, and it's still quite noisy. But they show the different data sets. I'll not show you all of them. They show little or no sign of flow disturbance at all. So this is the instrument to use, especially if you are on a shallow river and you can only measure a small portion of it, so that you depend more on the data you got. You don't need to screen out anything. And it's the same thing with the small trimaran and the big trimaran. And in front of the Zodiac or besides the Zodiac. So to sum up, like I just said, Stream Pro 1. The River Ray, the River Pro, and an M9 on either a trimaran or the remote control boat, they are probably okay. With the Rio Grande / Rio Pro in a trimaran or an arc boat, be careful. Don't go with what extrap says unless you are really certain that it shall be constant at the top, because there is a backbend definitely on the velocity profile using that. And the Rio Grande alone in a fixed mount, don't use it, and if you use it, be very, very careful with the extrapolation. And like we have seen, and I have said, both the boat and the instrument matters, but more the big instrument than the big boat. So that's it. Any questions?
Teledyne Marine. Everywhere you look.